I am new to physics, but I spent last 2 years trying to connect the mind-bending ideas of quantum mechanics to actual quantum computers, and my understanding was completely fragmented. I'm a keen student of the field, and last month I stopped searching for more explanations and started building one for myself. I used coding agents and AI to map out everything I was learning, connecting every isolated fact into one visual picture, a map of the entire field. Building it didn't just teach me the physics clearly, it completely changed how I process the news. Take a headline announcing a 1000 qubit machine. Before the map, I would have just been amazed. Now, I know to immediately ask, are they talking about physical qubits or logical qubits? Because physical qubits are incredibly fragile. A tiny temperature fluctuation is enough to crash them. That one distinction alone tells you whether a headline is a real breakthrough or just marketing. But that one example is just scratching the surface. To really understand where this industry is going, we need to look at the entire stack layer by layer.
So, how do you read the map? Treat it like a page of writing, left to right, top to bottom. 4 rows all interconnected, flowing logically in one direction. The first row is the ideas, the unique physics which makes basic of quantum computers work. The second row is how you turn that physics into actual computation. The third row is the hardware, the messy business of building a real machine. And the bottom row is what it's all for, the payoff, the business and current state with limitations. So, let's go. We're in the top row now. This is the physics row. And I want to promise you something up front. You do not need a degree for this part. The math exists, and it's real, but the ideas are things you can hold in your head. Every field has an origin story. And this one starts, of all things, with a complaint. Richard Feynman looked at this situation and said something that was half joke, half prophecy. In 1981, he basically said, nature is quantum, and our normal computers can't keep up, and stop being stubborn. Build the computer out of quantum parts too. Fight fire with fire. Use quantum physics to simulate quantum physics. It was a throwaway line at a conference, and it became the seed of an industry. A physicist named David Deutsch took that seed and made it rigorous. He wrote down what a universal quantum computer would actually be, as a precise mathematical machine, not just a vibe. He gave the field its foundation, and then, in 1994, a mathematician named Peter Shor found a quantum algorithm that could break the encryption protecting the entire internet. And not in a vague one-day maybe sense, in a very specific way that would actually work. And that's when quantum computing stopped being a quiet physics curiosity and became something governments and companies threw money at. Nothing focuses the mind, or the budget, like the words, "This breaks all your secrets." Before we go further, we have to be crystal clear on one thing. What makes a quantum computer different from the laptop in front of you? And it comes down to the smallest piece, the basic unit of information. Your laptop, your phone, every computer you've ever used runs on bits. A bit is a switch. It's either a 0 or a 1, off or on, one definite value at a time. Everything digital is ultimately billions of these tiny, honest on or off choices. It's a beautifully simple idea. A quantum bit, or qubit, is not a switch. And this is the first place your intuition has to stretch a little, so stay with me. Picture a globe. A little arrow sticking out from the center, pointing somewhere on the surface. If it points straight up to the North Pole, that's a 0. Straight down, South Pole, that's a 1. So far, it's just a fancy switch. But the arrow doesn't have to point straight up or straight down. It can tilt. It can point at the equator, or anywhere in between. And when it's tilted, the qubit is holding a genuine blend of 0 and 1 at the same time. Physical qubits are actual particles like trapped ions, semiconducting circuits, atoms in superposition. One qubit is mildly interesting, but qubits combine in a way switches never could. 2 qubits track 4 possibilities at once, 10 qubits trap a mountain, and it keeps doubling. By the time you have around 300 qubits, they're tracking more possible states than there are atoms in the entire observable universe. Let that sit. 300 of these things. Not 300 billion, 300. And they already outnumber the atoms in everything you can see. That explosive doubling is the entire source of the quantum computing's power. That blended state, the tilted arrow, has a proper name: superposition. And the thing I love about it, the thing that makes it real physics instead of mysticism, is that it's not fuzzy. It comes with exact, predictable odds. Go back to the arrow on the globe. The angle it makes, how far it's tilted from the North Pole, sets the probability. Point it straight up, and you'll read a 0 every single time, guaranteed. Tilt it down to the equator, and you get a perfect 50-50, like a fair coin. Tilt it a little past that, and maybe it's 70-30. The direction of the arrow literally is the probability. There's a clean little formula underneath, but you don't need it. The picture carries the whole idea. Angle equals odds. Now for the problem in quantum computing is a big engineering problem. This tilted arrow is incredibly delicate. A superposition only so vast that a qubit is left completely alone. A tiny bit of heat, a faint vibration, a stray magnetic field drifting past, and the arrow collapses back to a boring up or down. The state just falls apart. The length of time you get before that happens has a name: coherence. And I want you to remember that word, because stretching out coherence, buying a few more microseconds, is most of what quantum hardware engineering is. Billions of dollars, thousands of PhDs, all fighting to keep a tilted arrow tilted for a little longer. One clever trick from 2023 doesn't fight the collapse, but manages it, turning certain failures into flagged, visible ones you can catch the instant they happen. That kind of small, unglamorous advance is what real progress looks like here. Now we can connect two qubits together, and we meet the idea that even bothered Einstein: entanglement. You have to read and understand detailed mathematics, etc. But why we need entanglement in quantum computing is that it forms a very unique system. When two qubits become entangled, they stop being two separate things. Imagine two coins that are entangled. Look at either one alone, and it's a random 50-50, no pattern at all. But look at them together, and they always match. Always. Even if you carry one across the room or across the country. Neither coin has a secret answer hidden inside it. The answer only exists in the relationship. It's stored in the connection between the qubits, in the correlation. Einstein hated this. He called it spooky action at a distance. He was right, but it's spooky. He was wrong, but it wasn't real. Experiments settled it, and the people who ran them won the Nobel Prize in the 2022. The simplest entangled pair is called a Bell state. Stretch it across many qubits, and it's called GHZ. These are the everyday workhorses of the quantum field. Entanglement is the ingredient that makes quantum hard to imitate, and it doesn't stay trapped on one chip. You can send entanglement down an optical fiber. The seed of what people call the quantum internet, and it's the reason telecoms and governments are paying attention. So now we've got two big ideas, a huge space of possibilities from superposition, and qubits woven together by entanglement. But there's a missing piece. How does all that turn into an actual answer you can use? The answer is interference, and it's the cleverest part of the whole thing. Think about waves, ripples on a pond. When the crest of one wave lines up with the crest of another, they add together into a bigger wave. When a crest meets a trough, they cancel out, and you get flat, still water. Quantum possibilities behave exactly like these waves. They can add up, or they can cancel. The trick is this, and once you see it, the whole field clicks. A quantum algorithm is choreography. You carefully arrange the calculation so that all the paths leading to the wrong answer meet crest to trough and cancel out to nothing, while all the paths leading to the right answer add up and get loud. You're not checking every possibility one by one. You're setting up a wave pattern where the correct answer is the only thing left standing. That, right there, is how a quantum computer computes. The thing that controls all of it is a hidden quantity called phase. It's the invisible timing of the wave, the thing that decides whether two waves add or cancel. Every quantum operation is really just nudging phase around. And that's also why the hardware's worst enemy has a name: phase noise. As you pack more qubits onto a chip, they start accidentally bumping into each other and leaking, and that scrambles the delicate timing that interference depends on. Keep that in mind. When we get to the hardware, half the struggle is just protecting phase. One more idea to finish the top row, and it's the most counterintuitive of all: measurement. Everything we've talked about so far, the tilted arrows, the entangled pairs, the wave patterns, all of it happens hidden, inside the machine where you can't look. Measurement is the moment you finally look, and it comes with a hard price. The instant you read a qubit, its beautiful tilted arrow snaps to a definite answer. Just 0 or just 1. All that rich in between, gone the moment you peek. And the answer you get is random, weighted by the odds the arrow is carrying. This is deeply weird, so sit with it. You can run the exact same program twice and get two different answers, and nothing was broken. That's just how it works. You run it many times and read the pattern. This next part shapes how every quantum program is written. Collapse is a one-way door. You cannot unlook. Once the arrow has snapped, the superposition is gone for good, no recovering it. That's why real algorithms do all their quantum work first, in the dark, and only measure at the very last step. You protect the delicate stuff until the final moment. The one exception, and it's an important one, is that sometimes collapsing a few qubits early and reacting to what you read is exactly what you want. That real-time feedback loop is the beating heart of error correction, which we'll get to in the hardware row. And that's the physics. 6 ideas. Entanglement weaves it together. Interference turns it into an answer. Measurement reads it out. If you followed this far, you understand more about quantum computing than many gurus. Now let's put it to work. Second row. We're leaving the pure physics behind and asking a practical question. Given these strange ingredients, how do you actually build a program? How do you get from spooky arrows to something that factors a number or designs a molecule? If the ideas in the top row are the physics, then gates are the instruction set. They're the verbs. And the surprising thing is how few you actually need. One gate takes a plain, boring 0 and tips it into superposition, that 50-50 tilted arrow. That's almost always the opening move of any program, the moment you switch the quantumness on. A few more gates rotate a single qubit around, aiming the arrow wherever you want it. And then there's the important one, a 2-qubit gate called C-naught. It flips one qubit depending on the state of another, and in doing so, it creates entanglement. It's the gate that ties qubits together. And a payoff is a small miracle. Those few gates are enough. With just single qubit rotations and that one entangling gate, you can build any quantum program that can exist. And at the very end, a measurement reads the qubits back out as ordinary zeros and ones you can actually use. Now we get to the big one, the algorithm that started the funding stampede. This is worth slowing all the way down for, because if you understand this one, you understand why everyone, including governments, are paying attention. Almost all of internet security rests on one lopsided fact about numbers. If I give you two large prime numbers and ask you to multiply them, that's easy. A computer does it instantly. But if I hand you only the answer, the big product, and ask you to work backwards and find the two primes that made it, that's brutally hard. For a big enough number, every computer on Earth working together would take longer than the age of the universe. That one gap, easy to multiply, effectively impossible to reverse, is the lock that secures your bank login, your messages, your credit card. It's called RSA encryption. Peter Shor found the key to this lock, and his insight was sideways and brilliant. He showed that factoring is secretly the same as finding a repeating rhythm, a hidden period in a pattern. And finding a hidden rhythm is exactly the kind of thing quantum interference is spectacularly good at. Those canceling waves we just talked about find the pattern almost effortlessly. The result? A problem that would take longer than the universe has existed collapses down to something a quantum computer could do in hours. Longer than the age of the universe, down to an afternoon. That's the whole reason a single algorithm from 1994 is, right now, forcing the entire security industry to rebuild itself. We're going to follow that thread all the way to the bottom of the map. Now, Shor gets the headlines, but he's not alone. And this is where an investor needs to get pity, because the speedups are not all the same size. This matters. There's Grover's algorithm, which searches through an unsorted pile of things much faster than any classical method. It squares the root of the problem, it doesn't make it vanish. Anyone promising you Grover will instantly solve everything is stretching. Then there's the quantum Fourier transform, which is the actual engine that made Shor work, the thing that finds those hidden rhythms. And there are the hybrid methods, with names like VQE and QAOA, which use short, shallow programs and lean on a regular computer for help. Those matter enormously right now, because they're the ones that might do something useful on the noisy, imperfect machines we actually have today, rather than the perfect ones we're still waiting for. And there's one, called HHL, that promises to solve gigantic systems of equations exponentially faster. It sounds incredible, but the fine print is heavy. All sorts of conditions have to line up, and in practice, it's much harder to use than the headline suggests. I mention it because exponential speedup gets printed on a lot of pitch decks, and the asterisks usually get left off. This next node is where a lot of hype goes to die, and I think it's the most valuable thing on the whole map for anyone with money on the line. So listen closely. Quantum computers do not make everything faster. They don't. There's a specific family of problems, and computer scientists have a name for it, BQP, that quantum machines handle very well. Factoring lives there. A handful of chemistry and physics problems live there. But the famously hard problems, the ones businesses actually wrestle with every day, the giant scheduling and routing and packing puzzles, those are a different family, called MP. And the scientific consensus is that quantum computers are not believed to crack those in general. So, the sober takeaway. Quantum's advantage is narrow and sharp. It's extraordinarily good at a small number of specific problems, and close to useless on most others. When someone tells you a quantum computer will optimize your entire supply chain or instantly train any AI, that's not what the mathematics promises. The real opportunities are narrower, and knowing exactly where they are is worth more than any amount of enthusiasm. You can program a real quantum computer today, from your laptop, for free. IBM's tool called Qiskit is where most people start. You write circuits in Python, the same ordinary language millions of developers already know. Google has its own version called Circ. There's another, Penny Lane, that treats quantum circuits like trainable neural networks, which is how the quantum and AI worlds are starting to touch. Several companies rent out real quantum hardware over the internet by the shot. You send your program, it runs on an actual quantum chip somewhere, and the answers come back. Third road, the hardware road. And this is where the dream meets the workshop. If you're weighing where this industry actually stands, this is the road to study hardest. First, a fork in the road that most people don't even know exists. The gate and circuit approach we just described, the step-by-step instructions, is the mainstream, the default. But it is not the only way to compute with quantum mechanics. There are rival philosophies. There's measurement-based compute, which works almost backwards from what you'd expect. You build one enormous entangled state up front, and then you run the entire computation just by choosing what to measure and in what order. There's annealing, which doesn't use steps at all. Instead, it reshapes your problem into a landscape of hills and valleys. So the answer you want is the lowest valley, and then it lets the physics roll downhill and settle there. And there's the topological approach, the most exotic of all, which stores information in the way exotic particles braid around each other. So the information is protected from noise at the deepest level. Now the honest, messy heart of the matter. Nobody agrees on what to physically make a qubit out of. And I don't mean that as a criticism. I mean it's a live, expensive, unresolved contest, and where you land on it is basically on investment pieces. Let me walk you through the main horses in a race. Superconducting circuits, chilled to a hair above absolute zero, colder than deep space. They're fast and may play nicely with chip fabrication. That's the path IBM and Google are on. Neutral atoms, held in place by grids of laser beams acting like tweezers. Every atom is perfectly identical, courtesy of nature, and they pack in tightly, which is how newer companies leapt past 1,000 qubits so fast. Trapped ions, individual charged atoms held by electric fields. These are the quality champions, the cleanest operations and the longest coherence, but they run slower. Silicon spin qubits, which try to piggyback on the trillion-dollar chip industry we already have. And photonic qubits, which compute with individual particles of light, naturally sturdy and even room temperature, but famously hard to make interact with each other. So, the question the entire field is built around, how do you make something reliable out of parts this shaky? And the answer is the most important idea in this whole third row. So let me get it room. This is the real finish line. The core trick is this. Instead of trusting your precious information to one fragile qubit, you smear it across many of them, so that no single failure can destroy it. It's a bit like telling a secret to a whole crowd instead of one person, so that even if a few of them forget, the group as a whole still remembers. Very roughly, somewhere between 100 and 1,000 physical qubits work together to protect just one truly reliable qubit, which we call a logical qubit. Now the neat part. You can't just look at the qubits to check them for errors, because looking, measuring, would collapse them and destroy the very thing you're protecting. So a scheme called the surface code checks only the relationships between neighboring qubits, catching errors without ever reading the protected secret itself. And there's a magic threshold, a tipping point. Below a certain error rate, a beautiful thing happens. Adding more qubits makes your logical qubit better instead of worse. Above it, more qubits just means more mess. For 30 years, that threshold was theory, a promise on a chalkboard. And then in 2024, Google put a chip on the correct side of that line and showed it working. That's the result that shifted the mood of the entire field from hope to belief. It's the single most important experiment of recent years, and it's the reason the roadmaps you'll see at the end of this map suddenly got a lot more confident. Let's name where we actually are today, because it's easy to get lost between the headlines and the hype. There's a word for the current era, NISQ. It stands for Noisy Intermediate Scale Quantum. Translation: machines with tens to a few hundred qubits, still too noisy to do full error correction. Powerful machines, but flawed ones. That's the honest status today, and it's what exists. In this in-between era, you lean on a stopgap called error mitigation. It doesn't fix the errors. Instead, you run your noisy program many times, and use clever statistics to estimate what the clean answer would have been. And one lesson that matters: stop trusting qubit count as the headline number. It's misleading, and sometimes deliberately so. A handful of excellent qubits will beat a huge pile of sloppy ones every time. The best operations today hit about 99.9% accuracy, and the field has built smarter scorecards, with names like quantum volume, that fold quality and speed together instead of just counting heads. When you evaluate this industry, quality is the number to watch, not size. So who's actually in this fight? Because nobody has won, the industry right now is a spread of competing bets, and it's worth knowing who's wagering on what. IBM and Google lead the superconducting path, with the highest qubit counts and the most detailed public roadmaps toward the fault-tolerant future. IonQ and Quantinuum took the trapped ion road, competing on quality rather than raw size. Qubera and Pascal are the neutral atom newcomers, the ones scaling the fastest. PsiQuantum and Xanadu are betting the whole company on photonics, on light-based qubits eventually reaching millions on manufacturable chips. And then there's D-Wave, which went its own way years ago and sells annealing machines today, aimed narrowly at optimization. Not a universal computer, but real hardware with real, if modest, revenue right now, bottom row. The business and application of quantum in its current state. We've done the physics, we've done the programming, we've done the brutal engineering. Now the question that actually matters to a business: what is any of this for? And just as importantly, where is the hype outrunning the truth? Let's separate the real from the sales pitch, one by one. Let's start with the promised land, the applications. And I'm going to be careful here, because this is where the exaggeration is thickest. The strongest, most believable bet is chemistry. Simulating molecules and chemical reactions is a naturally quantum problem, which means it plays directly to a quantum computer's real strength, the one place where the math is on your side. Better batteries, better fertilizers, better catalysts, maybe better drugs. This is the near-term win most experts actually agree upon. If you want to know where the first real value shows up, it will be chemistry. Optimization, the logistics and finance pitch, is the one you'll hear most from salespeople, and it is doubtful. The problems are real and valuable, but as we saw in complexity theory, the proven quantum speedups here are uncertain and often small. Machine learning is the loudest area of all, and honestly, the one I trust least right now, because several early quantum beats classical claims got matched by ordinary computers a year or two later. And then there's security, which is quantum's biggest impact already, today. And the strange thing is, you don't even need a working quantum computer to fuel it. Which brings us neatly to the next three topics. Quantum mechanics doesn't only threaten security, it can also protect it, with a guarantee that comes from the laws of physics rather than the difficulty of some math problem. The founding idea is called BB84, and it's clever. You send an encryption key encoded in individual qubits, and because of that measurement rule we learned that looking at a quantum state disturbs it, any eavesdropper who tries to intercept the key must measure it, and measuring leaves fingerprints. So the two honest parties can always tell if someone was listening. The security isn't "this math is hard to crack," it's "the universe will rat out the spy." That's a fundamentally different, stronger kind of promise. Entanglement enables an even stranger feat, with the science fiction name of teleportation. It moves a qubit's exact state to a distant location using shared entanglement plus an ordinary message. No particle makes the journey, only the information does. And this has already left the laboratory. China's Michia satellite shared entangled photons between stations more than 1,200 kilometers apart. This is real infrastructure being built now. Now, the node that touches you personally, probably this year, even though a big quantum computer doesn't exist yet. Stay with me, because this is the most immediate real-world consequence on the entire map. Remember Shor's algorithm, all the way back in the second row. A large enough quantum computer running it would break the encryption behind web traffic, banking, digital signatures, the lot. And the chilling part, the reason this is urgent today and not in some hazy future. It's called harvest now, decrypt later. An adversary doesn't need a quantum computer today. They can simply record your encrypted data now, today, and sit on it, and wait, and decrypt it in 10 years when the machine finally exists. Which means any secret that still needs to be secret a decade from now is, in a real sense, already exposed. So the world is not waiting. In 2024, the US standards body NIST chose a new generation of quantum-safe encryption, built mostly on a kind of math involving lattices, but it's believed to be hard for quantum and classical computers alike. The hard part now is scale. Every browser, every server, every stored secret has to be upgraded. It's one of the largest security migrations in the history of computing. It's already underway, and it will take years. If you want a place where quantum is creating real work and real budgets right now, this is it. Before we reach the roadmap, I want to stop on the one payoff that almost everyone skips, and it drives me a little crazy that they do, because it's the one that already works and already cites: quantum sensing. While everyone argues about quantum computers, quantum sensors are already out in the field, beating their classical rivals today. Optical atomic clocks keep time so precisely that they would lose less than a single second across the entire 14 billion year age of the universe. That precision is what underpins GPS. Every time your phone finds you on a map, you're leaning on this physics. Atom-based gravimeters sense minuscule changes in gravity, precise enough to find tunnels, pipes, and water hidden underground without digging. And diamond-based magnetometers detect magnetic fields so faint they can watch individual neurons fire inside a living brain. This is not someday technology. It's a working, revenue-generating corner of the quantum world right now. If you only remember one underhyped opportunity from this whole map, make it this one. Which brings us, finally, to the road itself, and where the people building this say it's headed. The machine era really opened in 2011, when D-Wave shipped the first commercial quantum computer, that specialized annealer. 2019 gave us the first "we beat classical" claim, with Google's Sycamore. And 2024 gave us the big one, error correction crossing that magic threshold. The result that changed the mood from hoping to believing. And a target now written on the board is around 2029. IBM is openly aiming at a fault-tolerant machine it calls Starling, and Google and others are chasing million-qubit roadmaps behind it. This coming stretch, the late 20s, is what people are calling the decade of logical qubits. Let's pull all the way back out and look at the whole map one more time. Before you close the map, I owe you one honest stop. We just pulled back and looked at the whole thing, and it really is beautiful. But it would be a disservice to leave you on that high note without saying plainly how far there still is to go. So here it is, the reality check. In January 2025, the man who runs the world's most valuable chip company stood on a stage and said out loud that genuinely useful quantum computers are probably 15 to 30 years away. 20, he said, was a good guess. Quantum stocks fell hard that same day, tens of billions of dollars gone before lunch. And the deepest reason for that caution isn't money, it's physics. Remember the split between physical qubits and logical ones. Today we can build machines with hundreds, even thousands of noisy physical qubits. But the error-corrected logical qubits, the reliable kind that can actually carry a calculation all the way to the end, we have only a handful. A real run of Shor's algorithm, the one that breaks encryption, would need thousands of those logical qubits, which in today's terms means millions of physical ones. We are nowhere near. Behind the physics sits an engineering wall. Every single qubit wants its own control wiring, its own microwave line, its own slice of cooling to a hair above absolute zero. Going from 1,000 qubits to 1,000,000 puts brutal strain on the refrigerators, on the cabling, and on the ordinary classical electronics that steer and read the chip. At that scale, the planning is every bit as hard as the quantum mechanics. The money tells the same story from another side. Governments and investors have poured well over $40 billion into quantum. Yearly revenue from quantum computing is still counted in the hundreds of millions, and most of that comes from cloud access, consulting, and sensing, rather than the big computing payoff everyone is waiting for. Almost every pure quantum company is still spending far more than it earns. So what would actually pull that 20-year guess closer? Honestly, 3 things. Qubits clean enough that you no longer need 1,000 of them to protect one reliable one. A workable way to wire up and connect millions of them. And a genuine killer application, an error-corrected algorithm with a clear commercial edge beyond the chemistry and sensing wins we can already point to. If we can land those 3, and the horizon stops looking like 20 years and starts moving toward us faster. None of this is a reason to look away. It's the reason to keep watching. A map is only worth keeping if it tells you the truth about the ground, including the stretches that are still under construction. So now you have the whole of it, the promise and the price, and you can read the next headline for what it really is.